Still with circular motion, now we're going to go around a banked curve. That is a curve that is at an angle. And in fact, most curves that you're travelling on, certainly on roads and things like that, are actually banked. Now, it's a very, very small banking on a lot of them, so you don't actually notice it. But there usually is a bit of a, well, sometimes you hear the word camber to the curve. I've obviously exaggerated a bit so I could have a diagram there. So imagine the banking is angled at theta, and that might be, say, the outside wheel of my car or whatever it happens to be. Good old Bob will put in the centre. Good old Bob. The forces. Well, because we're making contact with a surface, there's a normal force at right angles to the surface. And of course, gravity is still there. So in fact, the actual problem is very similar to the conical pendulum. It's just that the normal force has replaced tension. Other than that, it's the same problem, if you think about it. The horizontal forces are still going to be the centripetal force, so mv squared on r. So there's components of the normal. Okay, again with a bit of geometry we can show theta is in that position there. So horizontally we have n sine theta. So n sine theta is mv squared on r. Vertically, well, we hope the vertical forces are zero, so we're going around the curve, we don't want the car lifting off the ground all of a sudden. So n cos theta going up, mg going down. And you see we come up with the exact same equations as yesterday with the conical pendulum, just the normal force has replaced tension. So we can do the similar sorts of things. I can go, oh well, tan theta will be v squared on rg, and so on. So let's look at a problem. We've got a railway line, we're going around a curve that told us the radius of our curve, and the distance between the rails. Now, this is kind of important, because when you're driving a car, it's not that big a deal. I mean, if you drive too fast and say your car moves up the road or down the road because you're going too fast, not a big deal. But if you're in a train, there's a bit of a problem, because you don't want the train to derail. So if you're going too fast into that curve, then the train's going to want to move up the curve, bang, moves off the rails. That's not good. So we want to find the most favourable speed, so actually we'll stay on the track. So again, we draw up our problem. But this time I know, all right, the track is 1.5 metres wide, they've told me. And the outside rail, 0.08 above the inside rail. Put in our normal force and gravity. And we'll resolve, same as we always do. So horizontal forces, n sine theta, and that'll be mv squared on r. Vertical forces, n cos theta, that'll be mg. So back to our equation, tan theta is v squared on rg. We want to find v, or the speed to go around the track. Sine theta, I know, is 4 on 75. Remember they told me the distance up the track, which would be the hypotenuse, and the opposite. So we got 4 on 75. From there I can work out tan theta. If I was to draw up a triangle, it's 4 on the square root of 5,609. Summing all those numbers in, and we get 14.47, but remember the units when we're doing this is meters for length, seconds for time. Makes more sense to put that in kilometres per hour if we're talking about a train. And so 52 kilometres per hour for this particular curve. Alright, let's look at an old question. We've got a particle, mass m, travelling at a constant speed around a circular track, radius r, so it's our bank curve problem. You'll see there's the banking. They've told us the normal force. Now, there's another force put into play here, and that is this force called friction. Friction is a resistance. Okay, so it's in the opposite direction to the motion. Now, they've put it up the bank. It could go in either direction. It depends whether we're moving up or we're moving down as to which way friction would go. So they've just put it up for now. And they say it's in the range minus mu n to mu n, because as I say, it could be up, it could be down, so that's the negative and positive, one when it's going up, one when it's going down. Mu n will be, well, mu is a constant, and the normal force would be, yeah. And they've told us friction's positive when we're going up. Okay, so they've defined that for us. Gravity's G. They've told us the acceleration is v squared on r and directed towards the centre. So, okay, I think we've got enough information. Let's solve a problem. It says, by resolving our forces horizontally and vertically, show this wonderful expression. Okay. Well, if I'm going to resolve, I'm going to have to resolve the normal force and the frictional force. So I'll draw a couple of triangles there and work out where theta goes via geometry. So theta would be down here in the normal triangle. In the friction triangle, therefore, theta must be up the top there. We know all the horizontal forces will give us mv squared on r. So let's put those forces in. We'll have n sine theta going to the left, and friction F cos theta will be going to the right. We know those two added together will give us mv squared on r. Okay, and remember, the positive direction horizontally is towards the centre. Vertical forces, these will sum to give 0. We have n cos theta going up and f sine theta going up as well, and mg going down. So they all add to give 0. We should now be able to create this fraction. We've got the two things we need. N sine theta minus f cos theta over n cos theta plus f sine theta. Now, why on earth I'm doing it this way, I have no idea.
You just divided it.
Yeah. What a weird way of setting it out. But okay. The easier way would have just been to say mv squared on r divided by mg, which is what I've got. And that is, of course, v squared on rg. So, interesting way of setting it out. But we've got the answer. We've shown it is v squared on rg. The maximum speed that we're going to travel without slipping up the track is given by v squared max, and we're told that's tan theta plus mu on 1 minus mu tan theta, and we can suppose that mu tan theta is less than 1. Oh, that's nice of them. Okay. Why would that be?
So it can't be undefined. Oh, jokes.
Well, if it was bigger than... Oh, to make it negative, wouldn't it? Yeah, okay. Now, so I got to show that. Well, it's the friction that resists the particle moving up or down the slope. So if the particle is not slipping up, because it wants to slip up, friction must be maximum in the opposite direction. So for this problem, friction is acting down. But remember they said take up the plane to be positive. So the value of the friction is minus mu n. Minus mu n. Okay, so let's sub that in. We've worked out the v squared on rg, but we're talking about v squared max. That is now when friction is minus mu n. Substitute that in, and our n's will cancel. We're trying to get that expression up there. Looks like what I've got to do is divide everything by cos theta. That'll create the tans. If I divide everything by cos theta, sure enough it drops out. We get tan theta plus mu on 1 minus mu tan theta. Okay. If mu is greater than or equal to tan theta, or we've got to show that if it is, then the particle will not slide down the track, and it doesn't matter what the speed is. Okay, so what's the difference? We're now talking about minimum velocity. So the only difference now is the particle wants to slide down. That now means friction is acting up. So instead of being minus mu n, it'll be plus mu n. So we'll have exactly the same formula, except the sign will change wherever we had the mu n, which means I should end up with tan theta minus mu on 1 plus mu tan theta, because the sign of the friction has changed. So that's v squared minimum. They're telling us mu is greater than or equal to tan theta. Well, if that's true, look at the top of the fraction. That's going to end up being a negative number. V squared minimum on Rg, therefore, must be less than or equal to 0. Well, it can't be less than 0. So therefore, the minimum velocity is 0. Well, that's what we want. Because it's saying show that the particle will not slide down the track regardless of its speed. So we're saying the minimum velocity for it to not slide down the track is 0. So there's not a velocity we can put on it so that it will slide down the track. So it doesn't matter what the speed is, it will not slide down our track. Now, this was an interesting question, in that the circular motion is not horizontal, it's actually vertical. Because you've got this drum. Okay? So the drum's rotating, a particle P, so P is inside the drum. So imagine you're rolling this drum and a ball bearing or whatever it happens to be is rolling on the surfaces of the drum. So the drum will exert a normal force, but it will now be going towards the centre. Because it's making contact with the surface, it'll go away from the surface, and that will be towards the centre of the circle. So there's why it's directed that way. There'll also be, what else have they defined for us? There's a frictional force, because the ball will be rolling on the surface, so there'll be a resistance to that. That'll be in the direction of the tangent. I think that's all we need. We now have to find an expression for friction over the normal force, so F over N. To do this, I've just rotated the drum a little bit. I just find this a little bit easier because now friction looks like it's horizontal and the normal looks like it's vertical. It does, however, mean now when I resolve this horizontally and vertically, I'll have components of the gravitational force. The force is perpendicular. I can't really say horizontal and vertical because remember, that's not really horizontal and vertical. I've turned the picture. So I'm saying, let's look at the forces perpendicular to OP. And they will sum to be 0. Friction now is totally to the left, but I have a component of the gravitational force to the right. So I get mg cos theta minus f. So I come up with an expression for friction straight away. I don't have to worry about mucking about with the normal force. Now if I look at them parallel, circular motion, our resultant force is purely vertical here. We'll have the normal force going down, we'll have a component of gravity going down. So n plus mg sine theta will be mr omega squared. So n is mr omega squared minus mg sine theta. Okay, we want an expression for f over n. So now I can just substrate in. Mass divides through, and I get this g cos theta on r omega squared minus g sine theta. Okay, you can do it with the bank curve. I could do this same problem here too. So there's the bank curve problem, and we know we have the normal force, we have the gravitational force. Friction would go in one direction, whether it's up or down. But if I was to, again, rotate the problem, if I just wanted to find the normal force or the frictional force, then we'll get a component of the gravitational force, but this time the resultant force is not vertical or horizontal. Right? So remember, it would be horizontal in our original diagram, so when I rotate it, it's now going off at an angle. So there'll be a component of the resultant force, both what we're looking at as horizontal and looking at as vertical. So now I can say, well, the forces along the bank, that will be mv squared on r cos theta. And we have friction going to the left, mg sine theta going to the left. And we come up with an expression for friction. If I look at the ones perpendicular to the bank, the component of the resultant force would be mv squared on r sine theta. And we'll have the normal's totally up, component of gravity. And we get an expression for the normal force. Unfortunately, a lot of the time they tie your hands. And they'll give you this problem and they'll actually say things like, by resolving forces horizontally and vertically. So I'm not allowed to rotate the problem and do it the easy way, which is a shame. But if they don't mention that, you of course can. You need to find those forces.
Good, yeah.